Hello, everybody. Welcome back to our special session on energy here at the Fysikermøte. Our next speaker is Professor Axel Hjort of the University of Stavanger, and he's going to tell us about the science of oil and gas energy.
Okay, so thank you very much for inviting me to this symposium. And it's hard to follow up the brilliant talk that was right before me, but I would at least try to tell you a little bit about oil and energy. So the basic outline is first a little bit about myself, and then I'm going to tell you a little bit just basics so you understand some of the concepts. And then I would like to go into a particular case because I always think it's more interesting if you go into the details. And I was also hoping to make some commercial at the end. I'll try to tie our new master program to what I've been talking about. So I have a master and PhD in theoretical particle physics from University of Oslo. Halvsten Høgersen, professor, was supervisor for master thesis, and Jan Olav Egg on the PhD thesis. So my background is really far from what I'm supposed to be an expert in now. So I joined Rogaland Research, turned to IRIS North, and in 2011 I was the chief scientist. University of Stavanger, 2008, and in 2014 I'm professor in reservoir technology. And since 2013, I've been part of the management team for the National IOR Center of Norway, which is kind of it's a petro center similar to research based innovation center, 12 industry partner, roughly 50 million Norwegian kroner per year. And since 2019, I've been program leader for the computational engineering master program. So when Anders asked me to give this talk, the science of oil and gas energy is big topic. So, but roughly speaking, you can divide it into two, upstream and downstream. And I also see that Tor Bjørnstad has entered this slide. He should not be there, but anyway, I will talk about the upstream part of the oil and energy, which is how you get the oil and gas up from the subsurface. And I made some drawings because I couldn't find any good pictures, but just to kind of start out a little bit with the basics. So you have a platform and you have some reservoir down there, and we usually draw, you have water is the heaviest fluid, and then you have oil and you have gas on top. And if you look at the pressure versus the depth, you know that the water pressure, if we make it simple, increase due to gravitational forces. So when you go down, the pressure increases. And at some point where you have the oil-water contact, and if you ignore capillary forces, the pressure in the oil and water phase is the same. And what happens is when you are moving up from that line, because the oil is less dense than the water, the pressure decreases less. And someplace you meet then the oil and gas interface, and then the pressure decrease even less because the gas has a lesser density. And because of that, you have a pressure difference. So when you are drilling down from the rig down to the subsurface, you will have, in general, you will have a very high pressure in the gas phase compared to the water pressure, and you will have also higher pressure in the oil phase, and that is important for the recovery. So to make it very simple, in order to produce hydrocarbons, you need wells. If you have a gas reservoir, what you basically do, you just drill down, and because, as I explained, because of this really high pressure in the gas phase, you can just kind of lower, you can just produce the gas, and the pressure in the reservoir goes down, and you can kind of keep on producing without really doing much. For an oil reservoir, if you just take down the pressure, since oil is not so compressible, you cannot produce so much oil. It's very easy. You just drill a well and you take out the easy oil. And that I think happened outside of Vietnam by some companies that just went there, took out the easy oil, the pressures went down, and then just left. But in Norway, because we have this Petroleum Act, we are by law, we have to produce as much oil as possible as a benefit for the society of whole. It's not possible for companies to do that. So, and the real easy solution, at least offshore Norway, is that you replace the oil with a cheaper fluid. So in Norway, you inject seawater, and then seawater is left and you produce oil. So it sounds simple, but it's not really that simple because now you have multi-phase flow in porous media, and it's not really well described mathematically. And what tends to happen is that you inject water, and in some places you might displace the oil, as you can clearly see here. You get good displacement, but in some areas oil is left behind, and some places oil might not be produced at all. And you kind of have two problems. Even though water has passed through this zone, you have still oil left in the pore space, and this can be quite significant. And of course, you have areas where there's a lot of oil left. And the reason for this is something called wettability. That means that the rock has a certain preference to one of the two phases. Usually, the rock is a mixture between water and oil wet. And you also have scales, so you have you might have some big fractures in your reservoir, and that can let the flow will then channel through those big fractures. This is a graph that the Norwegian Petroleum Department publish each year, and it's quite interesting. What you see here is actually the fields on the Norwegian continental shelf. So the biggest is down there, Ekofisk, is at least one of the biggest. And what you can see is on the left-hand side, you see the gas that has been, or the hydrocarbons that has been sold. And on the right-hand side, you see what is left. And the dark green is actually what they expect to produce. So for the Ekofisk field, you see that there is actually significant amount of oil left. And actually for all the fields, there are a lot of oil left. And Norway still has more or less the world record in recovery. We are about 60%, which is very good. But still there is a lot of valuables left in the ground. And in order to kind of handle these problems, you need to understand what controls the release of oil from the pore space. So, and then scales become an issue. And what we are working on in the research, we are developing models to simulate flow from the very small scale up to the larger scale. So I have this rock here. This is typically what they do all the experiments on. This is a chalk, so it's basically like what you write on a blackboard with. And it looks quite solid, but it's actually the porosity is 50%. So it's 50% wide, and the oil is inside those pores. And this is typically what you do experiments on. So there's a lot of effort going into really understanding the role of the different scales. And we have mathematical tools where you can actually you can do the upscaling. But of course, as you see, it's all the way from nanometer scale down here and kilometer scale on the field scale. So it is it is a challenge, and maybe the most important struggle you have when you're going to really recover a field. So the center that I'm part of, we are working on all these different scales. So if you ask about, at least from my perspective, what the science of oil and energy is kind of, you have the different scales, and you also have different, you need people with different abilities. So you have experimentalists doing experiments on cores, like this, the one I showed. After the experiments, you need people that are able to tell you what actually went on inside the pores. So we have this Professor Udo Zimmermann, geologist, and then we have people from IFE doing tracer measurements, trying to inject tracers in the injection well and see where the flow is going. We have modeling people working with open source code, trying to do advanced gridding and really see simulate where the flow is going. I'm working on the upscaling part. And then we also have a huge task on automatic history matching. So you have all the data from the oil industry, all the production data, and you're trying to use the historical production data and then automatically update your reservoir model to reflect the uncertainty in those data. So uncertainty plays a big role, because you actually you don't really know what's in the subsurface. I mean, you have the needle points where the wells are, and then but now you also, in some wells, some fields, they have 4D seismic, so they can 4D is, for a physicist, it's a little bit annoying, because it's basically you take some images with a certain amount of time, so it's 1 year time lapse maybe, so it's not, but they call it 4D maybe because it's more fancy. But the question you always need to ask yourself is, does all of this understanding really lead to higher recovery? Because that's what the companies are interested in. I mean, and what I will hopefully try to convince you is actually the most important part is to really understand what goes on inside the pores. So I've been working with this for 8 years on all different scales, but my conclusion is, if you understand the mechanism, if you really understand what goes on the small scale, you are in a very good position to say something about what will happen on the really large scale. And so the understanding is important. Personally, I don't think that all the numerical modeling in between is that important. The companies put a lot of focus on it, but my opinion is that you can do quite well with simple models, but you need to understand. So we have put what I've been working a lot with, together with these 3 guys on the bottom, all of them have PhD in physics, is really to simulate pore scale flow, and not only the flow, but also the chemical interactions that happens inside the pore space and how that might affect the flow properties. So I want to talk to you about a specific case, Ekofisk compaction. Many of you, I guess, have heard about it. Maybe I will add something new to that story. So the Ekofisk field, as you saw earlier, is Norway's biggest oil field, really important. It's located right at our border in the sea. And they kind of started the production, or at least in the early 70s, and you can see some pictures here from 73 and 1984, and what you actually basically are seeing here. If you count the number of holes in this storage tank, you see that it has been sinking. And it's not really a big surprise why it's sinking, because what they did in the beginning was that they drilled down a well, and then they started to pull out fluids from the surface, and then the pore pressure goes down. So you have the weight of the overburden. The overburden, or the vertical stress, is simply the weight of everything above, and the reservoir is supported by the pore pressure. So when you remove fluids, the pore pressure goes down, and the effective stress, which is simply the difference between fluid pressure and overburden, it goes up, and then you get this compaction. But in this case, you also got seabed subsidence. So even though the reservoir was compacting, you got seabed subsidence, and that's of course a problem, because then the platform starts sinking, and it's expensive. And so they started the production by, the vertical stress is 62 megapascal, and if you just do the calculation, you just sum up the weight of the sand and the water and everything above, you get about 62 megapascal, and you can also do the hydrostatic gradient, and you find something similar to 48 megapascal pore pressure, and then you end up with a 14 megapascal effective stress. And then when you take down the pore pressure, you get huge increase in the effective stress, and it starts to compact. So these are some data showing that this is the average reservoir pressure going down, and this red line here is the subsidence rate. And this axis here shows you how much subsidence you have per year. So after the first production, it was about up to 40 centimeter per year, which is a lot. And then they increased the pore pressure by injecting water, and the subsidence went down as expected, but it is still surprisingly high. It's actually too higher than what you would expect. And so that was one thing they observed. Another thing they observed was that if they were looking in an observation well, the compaction rate. So this is cumulative, meaning that if it is a straight line, you have really no compaction. If it's more like a horizontal line, you have more compaction. But what you should just notice here is that this was an observation well, so they kind of logged everything in this well, and then they saw when they injected the water, they saw the waterfront passing through this injection well, and when after that water passed through, you saw a huge compaction. So this became this is what is known as water weakening, and we spend a lot of time on this. University of Stavanger, trying to understand this phenomena. So, and of course, if you understand it, you might be able to control it. And what you do typically in the lab, you have this core, you saturate it with a fluid, you put a small pore pressure on it, and then you put up some increase the pressure surrounding the core. And even though the stress regime is different in the reservoir, people tend to do these hydrostatic tests where you actually have the same pressure surrounding the core. So you raise this pressure, and then you measure how much the core is shrinking, and that's basically the strain. And what you measure is simply kind of when you increase the stress, you measure some kind of linear deformation. They call this the elastic phase, even though it's not fully elastic. But after a certain point, you go in, you have the yield point, and then you load it up to 10 megapascal, and you let it deform under constant stress, which try to simulate what's happening on the Ekofisk field. So, and it turns out that actually this yield point is dependent on fluid chemistry. And really nice paper by Rasmus Risnes, he was a professor here at UIS. He showed that, so try to illustrate here that you have grains and you have the pore fluid. So white is gas, this is fully saturated with oil, and this is with water. And this is a complicated graph, but if we only care about the x-axis here, that's basically the hydrostatic test where you have all the stresses equal and you just load up. And this point here is the yield point. And what you actually see is that if you have dry chalk, you have a yield point of 18 megapascal. And if it's water, it's close to 10, really showing that if you have different fluids inside the rock, you get different yield point. So they believe that, or they argue that this, the water actually leads to an additional pressure, which then act as a effective, acts as decreasing the cohesion between the grains. This was actually followed up in a very nice paper by Anja Rein and Dag Dyste from University of Oslo, where they actually showed that if you immerse calcite into different fluids, you can actually measure the fracture propagation speed, meaning you can measure how easy it is to create new surfaces. And they actually found that if you immerse it in completely oil, you have a much higher surface tension, or you need a much higher energy to create new surfaces than if you immerse it into water. And so by simply taking the yield point of dry and wet chalk from the previous graph, you get 1.8. If you assume that the yield point is kind of proportional to the energy that it takes to create new surfaces, you can make a similar ratio here, and you find that it's about 2.1, which I believe is a really nice explanation for the previous data. So what I would draw the attention to is that I think it's more to this story, because actually the grains are always, so historically the oil reservoir is filled with water and then oil enters. And due to capillary forces, you will never get oil into the grain contact. So we thought it was a little bit puzzling that if there is always water close to the grain contact, even if you have oil here, could this kind of, even if you replace the oil in the center of the pores, could you really explain this water weakening effect? And I'm not sure if this is the full story, but what we found out is actually that seawater at 20 degrees is much stronger than seawater at 130 degrees. So you get about 25 reduction yield, which is significant. And if you do the same experiments with a brine that is not supposed to do anything, similar to the formation water that was already there, you don't see any reduction in the yield point. Meaning that what we would argue is that it's actually interactions, adsorption on the pore surface that are causing additional pressure. And we were able to describe this with a disjoining pressure, taking into account adsorption of ions on the grain interfaces, changing the surface charge. Yeah. And we were also able to show that if you then also change the fluid chemistry, you can actually stop the deformation. So if you look at the x-axis here, it actually it's a test that has been running for 700 days. So if you change the fluid chemistry at 100 days, until 80 days. So this is a different fluid. So the yellow line is a different fluid. You actually are able to stop the deformation. Yeah. So my main point is actually here that you kind of need to understand the details, and if you understand the mechanism, which maybe we have done at least partly, you can also manipulate them. You can also do some changes, and then you might get other effects. I haven't told you about this, but when you analyze these lab data, we also observed that dissolution of rock was a really important part. But when translating this to field conditions, that didn't really seem to be so important. But the thing I told you about the surface charge is a really fast change that can happen quite far out in the field with in a short amount of time, and that seems to be more realistic. So I have a couple of more minutes. So I think as a physicist, we appreciate length scales. We understand those things. We teach our students how, and it's very well done in all our physics education. We start smaller scale, larger scales. We have we have effective laws on one scale, and we have more the fundamental laws on other scales, and students are really trained in this. What I think what we have learned also from this petroleum industry is that you shouldn't only build models to understand the mechanism always. I mean, it's always good to understand, but sometimes you should think about what is the models supposed to be used for. So sometimes we need to build models that are simpler because it will serve a certain purpose, and you can also more take into account the uncertainty part, and this is kind of the basis for the computational engineering master program, and I think that if you can, it's like with the previous talk, you kind of need some models that you need to quantify, and it will guide you what to focus on, what is correct and what matters, and you can also reflect uncertainty, and sometimes you just need very simple model, like simply making this correlation with the CO2 and the temperature, and the simpler models are often the most convincing ones. And of course, you should always have this in mind. All models are wrong, but some are useful. But it's also this last point here that you should really try to focus on what matters. Yeah, and we have now also been starting to look into how can we use this kind of modeling competence in other areas. And I think that the modeling skill is transferable. You can use part of what we have done in the porous media research and also apply to medical research. Of course, not all, but some problems. And we actually have, if any one of you know about a postdoc that wants to work with this, you should contact me, because we have now projects collaborating with the University Hospital of Oslo, and Norse is the project manager here. But we are basically using the same type of models, pore scale models, in this project as we have done in the petroleum. Yeah, I think right on time. So I think to produce a reservoir, or even if you're going to store CO2 for a long time or use it for hydrogen storing, you need a multi-scale understanding. But I think, if you're going to store something, for instance, CO2 for a really long time, you need to understand what happens on the pore scale, because that is what will say something about if there are some reactions leading to leakage, that will happens in the pro scale, and you need to understand those small scale phenomena. And I also think that physicists are perfect for working in this area, but I would also put some effort into the modeling skills, trying to model complex problems. Yeah, I think I will stop here. So thank you.
Thank you very much. If people have questions, if they could type them into the Q&A session on the Zoom. We already have one question, which is from Alexander. Is chalk a good representative for the properties of the rock that one encounters in the field? Your chalk there, yes.
Yes, very good question. Yeah, I mean, we have put a lot of effort into this. So I didn't say that, but of course, reservoir cores, where you drill down and take out the piece of rock of the reservoir, is extremely expensive, and the companies, they don't want to kind of waste these cores. So we have spent a lot of time drilling cores from different places and really try to quantify them to find out if an outcrop chalk core, which this is representative. So for the Valhall field, which is also a huge reservoir on the Norwegian Continental Shelf, and the Ekofisk field, we have analogs, but it is chalk. So the Ekofisk formation is chalk, and the Valhall formation is chalk. So I think we ended up with like the Stevens Klint from Denmark and Liège was good for the Valhall field. And then I think ConocoPhillips has decided that Kansas chalk, because it's close nearby them, is good for the Ekofisk field. Yeah, but that's clearly something you need to consider.
What was the name for ConocoPhillips?
Yeah, so the Kansas chalk.
Kansas.
So
right,
so it's but
US,
it's okay. So it's located closer to the head office of ConocoPhillips. But we like the Danish chalk. Yeah.
You also said that there is this law in Norway that requires as much of the oil to be extracted as possible.
Yeah.
And this apparently is not true in Vietnam. But is a similar process going on in the UK and in Denmark and the United States, that these kind of technologies are being used not just in Norway but in other similar countries?
I think that a strong government involvement, so we have the NPD in Norway, Norwegian Petroleum Directorate, and they kind of have one person sitting in each licenses, and they make sure that the companies producing the different fields, that they talk to each other. And so if they can see some synergies between different fields, they will, I mean, there is no force, but there is really good collaboration. In UK sector, they have a different model where I think the government goes directly into licenses and they make special tax regulations to try to encourage companies to test out new things. So I think there are kind of plus and minus, but I think what we have done in Norway, we should be really proud of, because it's a huge, we have really high recovery, good collaboration on the Norwegian Petroleum data website. You can find all the production data, and you can start making your own models and so on. So it's really, really good.